Hi, this is Mr. Weston. Today we're doing a video on rational exponent equations. So this is a tutorial video explaining how to do some of these more complicated looking equations, and we're going to show you that's not so complicated. So before you start, I would recommend having a calculator handy. I have one here. And then also, it doesn't say so. It gives you the instructions to solve each equation, but it doesn't tell you to check for extraneous solutions. That is something you're going to want to do. I don't think there's any extraneous solutions in these examples. Okay, so you're going to say, oh, why do I need to do that? Because you may encounter these in your own problems or on your quizzes and tests. So make sure you get into the habit of checking for extraneous solutions anytime you're dealing with rational exponents. So what is a rational exponent? Rational exponent is one that has a ratio, a fraction, for an exponent. Okay, so that's something to keep in mind. Anytime you're dealing with rational exponents or radicals, you need to check for extraneous solutions. Okay, so let me highlight that. Make sure you check for extraneous solutions. Now, before we begin, we need to understand like a big idea here. The big idea is we're going to use this concept. Anytime we raise a power to a power, okay, so if we have x to the a power and then we raise it to the b power, this is going to give us a to the b power. Or sorry, x to the a times b power. If you just multiply those exponents, when you raise a power to a power, you multiply exponents. Why does it work out like that? Well, if we have x squared to the third power, that's going to give us x squared times x squared times x squared. We're going to multiply x squared times itself 3 times based on that power of 3. Let's expand it a little bit. We know that x squared is the same thing as x times x. Okay, so I can do this 3 times. Now if I have x times itself 6 times, as you can see here, 1, 2, 3, 4, 5, 6, that's going to give us x to the 6. So what do? We multiplied the 2 and the 3 together to give us that power of 6. Why is that important? Well, let's take it to an example of rational exponents. If we have x to the 1/2 power, and we want to isolate the variable, we want to get it so it doesn't have anything going on to it, we're going to want that to be to the first power, because x to the first power is just x. So what could we raise the power to of inside the parentheses to make sure that exponent goes away? Well, check this out. What we're going to do is we are going to raise it to the 2/1. Why does that work? Well, when we raise a power to a power, we multiply exponents. So this becomes x to the 1/2 times 2/1. What happens there? We get 2/2, or if you like, do cross-canceling, and we get x to the 1/1 power. That's just x to the first power, or just x. We isolated the variable. Okay, so that's how you're going to do that. Using that principle, we're going to raise these powers, okay, of x to the reciprocal power. So that's something we're going to keep in mind. We're going to apply that principle to all these problems. Let's go ahead and start with number 4 because it's just like it, okay? So first off, we recognize that we have 1/2 power, so we're going to take both sides. This is a really tall parenthesis here, and we're going to raise it to the reciprocal. Now, if we do it to one side, we also have to do it to the other side. Okay, so we have r to the 1/2 raised to the 2/1. What happens? Well, these cancel off because we're multiplying powers here. Power to a power, multiply. We're going to get r to the first power, just r. Then we have 7 to the 2/1. That's the same thing as just 7 squared. Well, 7 squared is 49, so 49 is our answer. Now, we have to check for extraneous solutions. You're probably like, how do I do that? You just plug it back in, and if it comes up with a weird answer, something that doesn't make sense, for example, you might get something like 6 equals 5. That's obviously not a solution, okay? But if you get something that makes a true statement, then we're solid. So we have 7 equals, and then we have 49 to the 1/2 power. You're probably wondering, what does that mean, 49 to the 1/2 power? Well, anytime we have a fraction for a exponent, that bottom number in the denominator is technically our root. So I could rewrite this. Let me highlight that actually. We could rewrite this as the square root, because there's an implied 2 there. Okay, square roots have that implied 2. And then this is the square root of 49. Now that top number, that indicates the power. Okay, so this is the power. This is the root. As I said, there's an implied 2 there. And technically, we could raise this to the first power, but it doesn't change the value. Okay, so I'm just going to go ahead and write that because we're going to do problems where those are different. So I know the square root of 49 is 7. 7 to the first power just remains as 7. Does 7 equal 7? Question mark. And the answer is yes. Yes, it does. 7 does equal 7, and we're good. Okay, so that was a solution. Let's go ahead and show how this applies to different types of ratios. So a little bit harder, but same principle. I'm going to take this. x, and I'm going to raise it to the 2/3 power, okay? And I need to do that to both sides, 2/3. The whole reason why I do that is because all those are going to cancel out. I get x. Then I have 27. Now, how do I translate this? Well, if I have that 3 in the bottom, that means it's going to be a cubed root. And if I have that 2 on the top, that means I'm going to raise it to the second power. Okay, top number is power, bottom number is the root in terms of a rational exponent. So cube root, what I recommend doing is you could square, technically you could square the 27 first and then take the cube root of that. And since you got a calculator, it's not that complicated, but I always want to work smarter, not harder. So I'm going to take the cube root. I want to make this number smaller first and then square it. So something times itself 3 times equals 27. What is that something? Well, I know that something is 3. So the cube root of 27 is 3, and now I just need to square it, and that's going to give me my x. So 3 squared, 9. X is my answer. Check it. Okay, so I want to plug it back in. If I could do 9 to the 3 halves power, will that give me 27? This is my check. Okay, I'm going to go green for my check. What I can do here is that 2 in the bottom means I take the square root of 9, and then that 3 in the top means I can cube it. So I know the square root of 9 is 3, and then I'm going to cube it. Does that equal 27? And it does. 27 does equal 27. Okay, so kind of like an annoying second step, but it is necessary, okay? A lot of these are the same. I'm going to get to some a negative one right here. I'm going to do some of these tougher ones with some addition in there, and then I'll get to the second page, which looks a little bit more complicated, just a few extra steps. Okay, if you can handle multi-step equations, you can handle this. Let's go purple. I don't want to change color so much, so I'm just going to go purple. Now, what happens here? I got a negative 3/2. So if I have a negative, then I also have to raise it to its reciprocal, and the reciprocal means it's also negative. So negative 2/3 power. So I need to raise this to the negative 2/3 power. And when I'm going to describe what that means in just a second. So these cancel, okay? Long story short, those cancel. That's the whole point of multiplying by the reciprocal. So we get x equals, and then I have this to the negative 2/3 power. Now, anytime you have a negative exponent, this is tricky. Essentially what happens is we got to make it positive exponent first. In order to make it a positive exponent, we have to kind of change where the location is. Let me explain. So if I have x to the negative 1 power, that means it's 1 over x to the first power. And if I have x to the negative second power, that's 1 over x squared. Likewise, if I have 1 over x to the negative 3, that means it would be equal to 1 over x to the third power, which coincidentally means x to the third over 1. What does that mean for us? Okay, long story short, another long story. Anytime we have a negative exponent, it's going to change locations in our fraction in terms of denominator versus numerator. So this was technically in the numerator, that was technically in the numerator, and it moved to the denominator. It moved to the denominator and became positive. If it's already in the denominator, it's going to move to the numerator. Just change the location in the fraction, numerator, denominator. So if this is negative, we need to first rewrite it. So I'm going to rewrite it as a positive exponent. So 729, 2/3, but in order to make it positive, I had to change the location. Okay, think of it this way. It was feeling negative, so it needed to change its scenery, so it had to move to the other floor to become positive. So that's what it looks like. We just kind of switched the positions and still raised it to 2/3 power. You could put it like this. That's fine, okay? But really that 1 is not going to do us anything when we raise it to any power, okay? So I'm going to still put it in parentheses like this. Now, 729 over 1, we can simplify that. I said I wasn't going to change colors, and you know what I ended up doing? I changed colors. Whatever. So I have 729, and now I'm going to raise this to the 2/3 power. Here's another tip. You can either just raise the exponent on your calculator, 729, to the 2/3 power, or you can convert these to decimals. That one's not a good decimal to convert, but like something like 3/2, we could raise that to the 1.5, okay, x to the 1.5, or whatever we're raising on a calculator, 1/2, so 0.5. We could change it to a decimal. This one's not a good one to change to decimal. So the first thing I'm going to do, honestly, is I'm just going to do cube root of 729. And I think it's like 9 or 7, so let's find out. I'm not exactly sure. You can kind of use some predictive powers there. Now, if I could find my cube root, usually I use exponents. I'm going to go ahead and do that. So I'm going to go 729, and I'm just going to raise this to the, oops, something happened here. 729, I'm going to raise this to the 0.333333333 power. I could just do 0.666. Okay, it's 9. I was right. So it's 9. I just wanted to show you that we can take the cube root first. Let me show that. Cube root first, 729. I like making it smaller and then squaring it. So I got 9. So 9, and then I just square it, so I'm going to get 81. Okay, so 81 is my value for x, and I need to check it, so I'm going to do 81, and I'm just going to raise this on my calculator to the negative, and I'm just going to go negative 3 over 2. So 81 to the negative 3 over 2 power, is that equal to 1 over 729? And I might need to convert 1 over 29 into a decimal. So I'm just going to go 1.5 here. I called that negative 1.5. Okay, convert it to decimal, just make it easier to type in. 81 raised to the 1.5, negative 1.5. Okay, and actually what I saw is I got 1.5 and I got 729. So I know negative 1.5 is 1 over 729. So it checks out. Okay, it does equal. Okay, so that's checking for extraneous solutions. All right, I'm kind of limited on time. I'm going to try to hurry up and do a couple more of these. So kind of hang with me here. If you have a problem like this, the first thing you're going to do is you're going to add 1 to both sides. You want this radical by itself on one side of the equal sign. So I get 27 equals 27x to the 3/4 power. So what do I need to do? I need to raise all of this to the 4/3 power. It looks messy, but it kind of balances itself out. 4/3. So what happens? This all cancels out. We're left with 27x, and then we have 27 to the 4/3. Well, 27 to the 4/3 means I take the cube root first, and then I raise that to the 4th power. That essentially means 3 to the 4th power equals 27x. Okay, so that's going to be 81 equals x. Forgot the 27. Equals 27x. So I have to divide by 27. Okay, and when I divide by 27, I'm going to get 3. So I get 3 equals x. Check your answer, so I can plug in 3. 27 times 3. I'm just typing this into my calculator. Make sure you check for extraneous salutes, not salutes, for extraneous roots. So I get 3 times 27 equals 81, and then I raise this to the 0.75 power and plus negative 1, and it does. It checked out. Check. Check, check. All right, let's move on to some of these tougher examples. Most of them are pretty similar to what we've already been doing. One I want to address, this is similar to what we just did. You're going to raise this to the 3/5 power, like this, to both sides. Okay, and then you're going to have, it's a 2-step equation once you're done with that. You're going to have to add 1 and then divide by negative 18. So just keep that in mind for number 9. Very similar to what we just did. I want to talk about number 10 because it's negative, and this only applies to the a. So check this out. We are not going to do this like this, 6 power right away. We're going to try to get the exponent by itself. So I'm subtract 3 first. I get 2 equals 4a to the negative 1 over 6. Now, I don't raise it yet still because that negative 1/6 power is still only applied to a. It's not in parentheses here. There's a big difference. So I'm going to divide by 4 first, okay, to get the exponent by itself. So I cross that off and I get 1 over 2. 2 over 4 is equal to 1 over 2. A to the negative 1 over 6 power. Now, I'm going to raise everything to the negative 6 over 1 power. Okay? And that means I'm doing it to both sides. I just didn't want to write it twice. So what happens? I get a by itself on the right side. And then on the left side, I get 1 over 2 to the negative 6 power. Okay? What does that do for me? Well, now I need to raise to the negative 6 power, 1/2 to the negative 6 power. What I'm going to do first is I'm going to rewrite this as a positive exponent, okay? So that means I need to essentially flip it. 2 over 1 to the 6 power. That's what happens with the negative exponent. You flip it, okay? So then I have 2 to the 6 power equals a, and I think 2 to the 5th is 32, so that's going to give me 64 equals a. I don't know why I switched sides. Okay, so if I do 64 to the negative 1/6, that gives me 1 over 2 times 4 is 2 plus 3 equals 5. Check. It works out, okay? So that's one that's a little bit different just because it's not in parentheses. Let's see. I'm just going to look for another one. That looks a little tougher. Most of these are pretty much the same as we've been doing. Here's 115. This is not written in exponent form. Maybe we'll end on this one, or maybe do one more tough one with bigger numbers. Okay, so we'll do, this is our second to last one. I'm going to change this to an exponent first, but it's not necessary. Okay, so let's say you could change this to an exponent. I'm going to provide this option, 2m, and then this could be to the 1/3 power, and then times 5. You could change it like that first if you want to. Now, it's not necessary though. You're going to see that we could still just apply our rules of solving equations, trying to get the radical by itself. So we do 20 equals cube root 2m times 5. Okay, still not by itself. I'm going to divide by 5, trying to get the variable by itself. I get cube root 2m equals 4. Now, from here, if you want to undo a cube root, just like it would be if it was 1/3, you're going to raise it to the 3rd power. So raise it to the 3rd power. It gets rid of the cube root. I get 2m equals, I think that's 64. Divide by 2, and I get m equals 32. Okay, and then we can plug this back in when we're done to check our answer. So we do 32 times 2, 64, cube root 4. 4 times 5 is 20, plus 9, 29, checks out. No extraneous roots. Let's do one more. That's maybe looks a little difficult. Let's do this one with 3,000 here. Pretty much all these are the same though. So, a lot going on. We're going to subtract one first. Okay? We want to kind of handle this stuff last. Okay? So we're going to have 3645 equals 5 times 4r plus 17 to the 3/2 power. Still not by itself first. We need to divide by 5. I'm going to use a calculator here. I'm going to cheat. This is 3645 divided by 5, and I get 729. Okay. We've seen this one before. It was a power of 9, right? So we have 4r plus 17 equals, or sorry, to 3/2 power. I need to get rid of that reciprocal. Let me move this up. Okay, so I'm going to raise everything to the 2/3 power. So raise this to the 2/3 power, everything, everything, everything. So 729 to the 2/3, I think that's 9, right? And then we square that, it's going to give us 81. Yep. So that's going to give us 81 because I took the cube root of 729. We saw this earlier. If you want to just rewind if you're unfamiliar. So then this gets by itself 4r plus 17. Two-step equation now. So I'm going to subtract 17. 81 minus 17, that's going to be 64. 64 equals 4r. Divide by 4, and that should give us 16, right? Yes. R equals 16. 64. Yes. Okay. So we can check our roots. Do this whole process again. See, that's 64 plus 17. I just want to make sure we're doing everything correctly. Raised to the 1.5 power plus 1. I'm typing this on my calculator. Oops, I forgot to times 5. 729 times 5 plus 1. And I got checked out. Okay, no extraneous roots. So that's all there is to it. That's rational exponent equations. Hope you guys enjoyed this video. If you have any questions, make sure to leave a comment. I have tons of other playlists over Algebra 2 concepts and more. Make sure to check those out. Either way, I look forward to seeing you next time right here on Wes Explains Best.